All right, you guys, I got that it's time. The music finished right at the right time. I put up the question there, but I realized we did not actually finish the slides from Tuesday. So let's finish those really quickly. We've got like 2 or 3 more slides left to go here. Last time we were talking about how charged particles move through magnetic fields. And one of the things that we said is that it is what's called the Lorentz force, where you've got Q times the velocity crossed into the magnetic field. And so the force is always perpendicular to the direction of the charged particle's motion and to the direction of the magnetic field. And where this comes in handy is we said we can break up the velocity into parallel and perpendicular components to the magnetic field. And that's what you're seeing here is V sub, that little, I don't know what you would call that, stake in the ground. That's the sign for perpendicular. So V perpendicular times Q and B is going to be equal to the centripetal force, right? Absent of any other forces, we can say that since B is always perpendicular, the force is always perpendicular to the velocity, then you get something like this in the image here, where it's going to draw the particle into uniform circular motion if the speed and if the magnetic field stay constant. And what that allows you to solve for is R equals mv perpendicular divided by a quarterback. I mean the Q times B. So if you've got that there, especially if there are any chemistry majors in here, what very practical use does this phenomenon have for us? Does anybody know? We have an entire instrumentation set built around this phenomenon. If you've ever heard of a mass spectrometer before, this is what a mass spectrometer makes use of. It's the fact that you have M, the mass, and the charge Q, and for many different isotopes, you have very unique combinations of M over Q or Q over M. Specifically, you're looking for, chemists look for mass to charge ratio, which is M over Q. For some reason, physicists look for the inverse of that. We look for charge to mass ratio. I don't know why our 2 different disciplines of science look for the inverse of the same quantity, but we do. When I read chemistry papers or when my chemist students would bring information to me, it would always be mass to charge ratio. And when I read physics, it's always charge to mass ratio. But the idea is you can fire a stream of isotopes using different acceleration methods, and you fire that into a region of magnetic field strength B, and all of those different particles are going to curve at with some different radius. And where that strikes a detector plate gives you an idea of what the mass to charge or charge to mass ratio is. So mass spectrometers, they get more complicated than just this simple idea that I'm giving you here, but they're all based on the same premise. So recalling that the period of centripetal motion, T, is 2 pi r, so the circumference, divided by the speed with which you travel around the circle here, is going to be your period. We associate a characteristic frequency being 1 over the period, as being QB over 2 pi times the mass. So frequency is QB over 2 pi times the mass. What we did was we made a substitution here for R and V based on the previous slide, and we're able to get a quantity, frequency, that is independent of velocity and radius. B is magnetic field strength. Yes, question. It's okay. Right hand ruling it. It's okay. Don't use your left hand. It's false. It will lie to you. Yeah. It should be. I mean, B is rather magnanimous with magnetic field strength because, there's so many B's in the word magnetic. I mean, it makes a lot of sense, right? William, did you have a question? You can use your left hand if it's a negative charge. My recommendation is always use your right hand and let the sign tell you when you need to flip your result or not, because your left hand tells you lies. Don't listen to it. All right. Although it's not covered here, it's worth reading the rest of chapter 26 too. If you have any interest in fusion technology or the aurora borealis and space weather, if you have any interest in those whatsoever, I'm not going to cover it here, but the idea is you can squeeze magnetic field lines together, and when you do that, remember the density of field lines corresponds to the strength of the field. So when you squeeze it together and you go back to the previous slide, then what happens is, actually 2 slides ago, as you increase magnetic field strength, the radius gets smaller, and it's going to have to end up traveling faster to do so. It ends up more and more of the velocity has to be directed perpendicular to the magnetic field strength, and you can end up getting a particle that will bounce back and forth between pairs of bunched magnetic fields. And it's a way that we thought for a long time that we could do magnetic or nuclear fusion, but that has failed us because it requires so much energy to push those magnetic field lines together to cause the fusion to happen in those regions. But in terms of space weather, it's pretty cool. So check it out if you're interested in that. Other things that are covered that are good for you to look at in case you're interested from a chemistry standpoint are the magnetic bottles. We already talked about that. Velocity selectors. That's going to be something that we're going to not really talk about just in terms of slides, but we'll do some problems with velocity selectors. Charge to mass ratio, if you are interested in particle physics or interested in chemistry. Mass spectrometers, if you're interested in chemistry. And cyclotrons, well, cyclotrons are just cool, so just look them up. They're in the rest of chapter 26. And with that, I think I'm ready to take questions based on the discussion that we had Tuesday, if you remember back that far, or what we've talked about so far today. The first question I expect to get is, yes. Can I put the QR code back up? Yeah, I'll put the QR code back up. So while y'all are doing that, coffee order RN. I don't know what RN stands for, but what? Right now. If I could have any coffee in the world right now, it would be from a coffee shop in Searcy where Harding was. It was called Mr. Postman. So they mailed things out, but they also did coffee, and they had something called a smokin' mocha. It used spicy cinnamon and inside of a mocha, and they mixed it together. And I've not found anyone else ever who can make it. Everybody, they'll do Aztec mochas, which is with cayenne pepper. They'll do other things, but nobody makes the smokin' mocha like they do. Now, that's my coffee order right now. If I were to tell you how I normally drink my coffee, I'm very particular. I've gotten to where we are using a coffee subscription service now, so I get a dark roasty bean, typically with hints of chocolate. I like it with where it's fresh ground, so I'll grind it in the morning, usually a fine ground, and I'll do it with AeroPress. I don't do it at the recommended temperature of 205 degrees. I do it at about 185 degrees because it doesn't bring out the bitter notes quite as much. And I do it with the espresso style, and I'll froth my own cream using a cream frother, and then I'll pour that. Generally, I try to get at least a little bit going in the side so it sits on top and the rest goes in directly, so that way it mixes in with the coffee. Add a little bit of cinnamon sugar on top. I make my own lattes every morning, and I am very spoiled, and it's awesome. Yeah, it's a whole process. It takes me about 3 or 4 minutes to do it, but it's a really excellent way to get the day started out. Where is wire C? That's a good question. If you multiply by the square root of -1, onto wire A or B, you'll usually find wire C. Bears, yes. Bears are a thing. So how, that one's, so how do wire shape, so how do wires shape? Wouldn't they want to make circles? Okay. Yeah, so one of the conceptual problems we're going to talk about actually is exactly this. If you have wires that are bunched up, wires generate their own magnetic fields, and if you could run enough current through that wire, then yeah, the wire is going to end up wanting to repel itself, and so it's going to end up wanting to make a circular loop of wire if the wire is flexible. Can you play Goofy Goober Rock at the start of the next class? I have no idea what it is, but I've still got my Spotify list open up here, so if you come down at the end of class, I can try to add it to the playlist. I watched the Veritasium video you mentioned last time, and it was very good. Who knew special relativity would be so relevant and commonplace? I love physics. More power to you. I appreciate that. Physics is awesome. But watch the videos. I will make sure that it gets posted to Canvas at some point. Are you referring to the prophecy of the chosen one? I'm too worried about the Wookiee, the droid attack on the Wookiees to worry about that right now. Thoughts on LeBron? He's a basketball player. Is there always an electric field associated with a magnetic field and vice versa? Can they be separated? So here's the thing. In our classical base class here, it is possible to have macro scale magnetic fields without macro scale electric fields. They can be separated from one another. But if you watch that Veritasium video that was posted on here, the problem is once you start traveling relativistically, a magnetic field will start to shift what it looks like and will look like an electric field. Electric fields and magnetic fields are just transformations of each other depending on what your reference frame is. So in a non-classical case, no, they are not separated. They are, again, two sides of the same coin. In a classical case, yes, they can be separated. Let's go back to questions here. Last three questions. Importance of quaternions in physics. Most of what we do in physics can be solved with Euler angles. If you are talking about the poles along the z-axis, then Euler angles will fail you, and quaternions become very, very relevant. Also, if you don't want to have to worry about quaternions are a much more specific way to denote angles. If you want to learn them, I think it's worth your time. I don't fully understand them. You should totally go through your Spotify likes. I don't know what that means. What? Like tell you what my most listened to songs are? Is that what you're saying? Oh, it's not a good playlist though, because it's full of movie soundtracks and I don't know, it's more instrumental than anything. So yeah, it's not as good of a playlist as the one that I curated for this class. The right-hand rule, just for finding direction of two vectors, not dotted into each other, but crossed into each other. The right-hand rule is for when you take the cross product between two vectors. It's also good for figuring out, well, I mean, this is still based on a cross product, but if you orient x and y in any direction, then take x and cross it into y, and it'll tell you the direction of z on a standard Cartesian grid. What else? We're going to use the right-hand rule, a different version of the right-hand rule, but it's still based off of the Biot-Savart cross product to find for a current what the magnetic field around that current looks like. So yeah, it is based on those. Let's move on to problems, and then we will come back and start a new presentation here shortly. So a point particle has a charge equal to negative 3.64 nanocoulomb and a velocity equal to 2.75 times 10 to the 3 meters per second in the I direction. Find the force on the charge if the magnetic field is 0.38 Tesla in J, and then you've got various combinations thereafter in B, C, and D. So let's do that really quickly. If you want to find the magnetic field strength, the magnetic force, don't forget that magnetic force F is equal to Q times V crossed into B. So I've got, in part A, the force is equal to the charge. The charge in this case is minus 3.64 nanocoulombs, times, let's see, A is 0.38 Tesla in the J hat direction, crossed into, let's see, well, no, I've got that backwards. Sorry, it's velocity first. 2615 is the problem. This would be from chapter 26, section 1. Let's delete this, and instead of doing what I was doing, we'll just move this over because we'll need it anyway. Whoops. And then the velocity is 2.75 times 10 to the 3 meters per second. And this is going to be an I hat. Now, there may have been several different ways that you've learned how to take the cross product. I think we talked about it a little bit last semester. But one way to take the cross product is you can say that for a vector C, where C is equal to A cross B, one way to find C is you take the magnitude of A and B and multiply them together, and then take the sine of the angle between them. So B might look something like this, and A might look something like this, and the angle between them is going to be theta, but then you have to multiply by the normal vector to both. The normal vector to both, meaning perpendicular to both, is going to look something like this right here. So that's one way to do it. But oftentimes you're not going to know what the normal vector is here. In this problem, it's actually quite simple to solve. You know that I crossed into J. I, J, and K, one of the things that we talked about, live in a cyclic relationship to each other. So you've got I crossed into J gives you K. J crossed into K gives you I, and K crossed into I gives you J. So start at 1, you'd start at I hat, multiply onto J hat. That means our answer is going to be in K hat here. Okay? And also note that any vector crossed into itself is the null vector. It's 0. So that's going to get you most of the way that you need to go. A more robust way to do it, if you have your vectors have components in, both vectors have components in x, y, and z, one way that you can do it is if you want to know what c is equal to, let's not do it over here. In this case, c is going to be equal to the determinant of the matrix, I hat, j hat, and k hat, where you've got a x, a y, and a z, bx, by, and bz. And what you'll do is you choose I hat, for example, and you start walking along the diagonal here. And what that tells you is, okay, I hat times ay times bz is how you would multiply that out. But then you have to consider, too, that there are backwards diagonals. So I can start walking backwards here, and I'd go down and to the left. I'd have to loop back around to az, and then down here to by. So I'd have minus I hat times az by. And then you'd have to add going from j hat down to az, down to bx, and then subtract off ax, j times ax times bz, and so on and so forth. If this is a little bit foreign to you, then pull up a video from, say, Khan Academy or 3 Blue 1 Brown explaining the cross product, because we're going to use that over and over and over again going forward through magnetism. So if you need a bit of a refresher, go ahead and take a look at that. But as far as this is concerned, our vectors are I hat crossed into j hat, which means our resultant should be in k hat. But don't forget, we've got this negative out front here. The final result for this one comes out to be minus 3.8 micronewtons in k hat. Okay? Now for part B, I get F is equal to the charge, so minus 3.64 nanocoulombs times 2.75 times 10 to the 3 meters per second in I hat, crossed into 0.75 Tesla onto I hat plus j hat. Let me ask you this. In what direction will the resultant be pointing? In plus or minus I, plus or minus j, or plus or minus k? Which one of those 6? It'll be in minus k as well, right? Because as far as the vectors are concerned, I have I hat crossed into I plus j hat. The cross product is distributive, so that's I hat crossed into I hat plus I hat crossed into j hat. Well, I hat crossed into itself is 0, and so I've just got I hat crossed into j again, which gives me k. I've got a negative out front, and this is basically going to be my magnetic field strength is essentially half or double what it was before, So I get a force that is roughly double what it was before. I get minus 7.51 micronewtons in K hat. What? No, I times I, if you take the cross product of parallel vectors, it's 0. Yeah. You can see that here, right? If A and B were parallel to one another, up here where I take C is equal to A cross B, then the angle between them is 0, and the sine of 0 is 0. Any other questions on these so far? Yeah, if there's any component of V that is parallel to the magnetic field, experiences 0 force. Which is evident here in part C, right? Yeah, what's the force on the charged particle? It's 0. Right? Because I have a velocity in I, and my charged particle is also moving in I. So 0 force. The last one, D, we shouldn't have to put any pen to paper, right? Because the only thing that's changed from D to B is that I still have the I hat component. We're going to experience 0 force from the I hat component, but then I've got the same magnitude of magnetic field strength in J, or what I had in J is now in K. And I crossed into K is going to be minus J. If you walk around this cyclic relationship backwards, you end up getting the negative of the resultant. So I crossed into K is negative J. Take the negative of that from the charge. So I get plus J is going to be the force. So F is going to be plus 7.51 micronewtons. But now it's going to be in J hat instead of K hat. So the sign of my charge is negative, but then I had I from my velocity up here in the top left crossed into K. I crossed into K is minus J times a negative charge gives me plus J. All right. The section of wire shown carries a current equal to 1.8 amps from A to B. The segment is in a region that has a magnetic field whose value is 1.2 Tesla in K hat. So my magnetic field B is going to be pointed in this direction right here. And it's going to be uniform as far as we can tell. So it's going to end up all over, oh my, what just happened here? Why does that always happen when I just want to paste a vector? So it's going to look something like this right here. If you can imagine that in the plane, or passing in front of and around and over my charge here. Right? So we said last time that the force on the wire is going to equal, let's see, I times L crossed into B. Where L is the length of the wire times the direction of the current. It's a negative or positive, but also in this case, let's say we're going to take it segment by segment. So we're going to break this right here and say the net force is going to be the force that's exerted on this piece right here, right? Plus the force that's exerted on this piece right here. And so I would have that L in this case would be 3 centimeters times I hat. And then for this segment, it's going to be 4 centimeters times J hat. But if the current was flowing in the opposite direction, it would be 4 centimeters times negative J hat and negative 3 centimeters times I hat. Yep. So let's call this segment 1 and segment 2. So the net force is going to be equal to the force on segment 1 plus the force on segment 2. So in this case, I've got the same current. The current is going to be equal to the 1.8 amps times the length. So that's going to be, let's see, 0.03 meters in I hat, crossed into a magnetic field that is 1.2 Tesla in K hat. And that's just going to be F1 here. In what direction do you expect this force to be? Pardon? Negative J. Yes, this will be a negative J. We've got, don't forget, a good thing to write down is I crossed into J is K hat. J crossed into K is I hat, and K crossed into I is J. But we have I crossed into K, so that's going to be minus J for that component. And then we have to consider that this is plus 1.8 amps times 0.04 meters in, let's see, J hat, crossed into 1.2 Tesla in K hat. So the resultant here, this piece is F2. The resultant here, J crossed into K, will be an I hat. And the result that you get is going to be 86.4 I hat minus 64.8 J hat, and that's going to be in millinewtons. So a very tiny amount of force on these wires, but non-zero. In fact, there's a great video that popped up because I'm a nerdy physicist and YouTube knows me. There's a great video that popped up where someone said, like, want a wire want to turn into a circle? Yes, if it's flexible, it will. But this one had an electromagnet where you could reverse the polarity of the electromagnet, and then he just had a suspended wire next to it. And what happens when, if you've got current flowing through the suspended wire and you turn on the electromagnet, there's going to be magnetic attraction between the electromagnet, the inductor, and the big loop, the flexible loop that you have. And so it ends up trying to wrap around the electromagnet. And then you reverse the polarity of the electromagnet, and it unwraps itself and then wraps itself around the electromagnet going in the opposite direction. So it's just a fun little experiment that you can do in the lab. Make sure you do it safely and that your wires are insulated, because you have to do it in terms of like 2 and 3 amps to see this effect happen. So not exactly currents that you want to be dealing with in an unsafe manner. Any questions on this one? just for completeness sake, in what direction on this graph here, in what direction would this force be acting on the well, what am I trying to say? On the wire segments here. Yeah, Henry. Yeah, so if you could draw this out, you're going to have a component of the force. I'm going to draw it from this point right here that is going to be down. And the portion that's down is going to be proportional to length 3. And then it's going to have a component that is in plus x. And it's going to have a component that is proportional to length 4. And so the resultant of the force is going to look, actually, let's try this right here. Try to draw it a little bit more parallel. There we go, something like that. The resultant of the force is going to be down and to the right here. It's going to look something like that. So it's kind of yanking on this thing. Any questions? Comments, concerns, valid criticisms, invalid criticisms? It's okay. It'll never be, whatever you ask in class will never be as bad as what gets said on SIEs. People are harsh on SIEs. What? The worst SIE that I ever got was my first semester at Harding. When you're trying to figure everything out and prepare course material for 3 different courses, one of my Phys 1 students spent 3 paragraphs explaining how I was the worst professor or teacher they'd ever had in high school or college, how I didn't know physics and I didn't know how to teach physics. It was the best advice I ever got. If you ever go into teaching and you're going to get your first semester SIEs back, make sure you've got a pint of ice cream next to you, or better yet, a quart of ice cream next to you. It makes it a lot better. Yeah. And it's really hard because you can have like 50 really good SIEs, but then you see that one student who is very frustrated about something, and it just completely rocks everything out of whack there. A 4.5 keV, kilo electron volt, remember that's going to be, actually let me ask you guys, keV, like what is that telling us in terms of the characteristic of this particle here? Why did it give us this obscure unit? Does anybody know? Okay, yeah, so it's energy, right? And this would be energy of motion. So anytime you see a particle having energy keV, it's just a more convenient scale to tell you what its speed is, right? So this would be its energy, specifically its kinetic energy, K. And K, we said, is equal to 1/2 mv squared. So it's just trying to give you an idea of what the particle's speed is. I guess it said that right there. Sorry, I didn't finish reading the question. Moves in a circular orbit that is perpendicular to a magnetic field of 0.325 Tesla. Find the radius of the orbit and the frequency and period of the orbital motion. These go right into, since it's already perpendicular, we don't have to draw this out, but I'm going to draw this out as B being out of the screen here. So B is going to look something like this, a uniform magnetic field coming out of the screen. And the velocity of the particle, let's say that the particle is here right now. in what direction, and let's say that the force, if this is executing centripetal motion, let's say it's executing centripetal motion about this point right here. So in what direction does the electron have to be traveling right now to be undergoing uniform circular motion perpendicular to the magnetic field in this case? Well, if you take V, and let's say that V is going down right now. If V is going down, then I cross out, I would get a force to the left, but remember this is a negative charge, so in this case, the electron has to be traveling up at this point, and that means it's going to execute uniform circular motion like so, in a counterclockwise fashion, at least the way that I've drawn it here. Not necessary to solve this problem because this does turn out to be a plug-and-chug sort of problem, but it's at least good to have some idea as to what's going on here, right? Because now what we said was in part A, if you want to find the radius of orbit, we found an equation that was mv perpendicular, which the velocity is already perpendicular here due to the problem setup, times q, divided by q times b. Well, we don't know what the velocity is, but we can solve it from the energy of the charged particle. And so v, the speed, is going to be equal to the square root of 2k over m. So now I've got that this is m over qb times square root of 2k over m, or that's going to be equal to the square root of 2km over qb. Don't forget that 1 EV is equal to 1.602. If you need this conversion on the exam, it'll be on there, times 10 to the minus 19 joules, if we want this in standard SI units. So that means our radius is equal to the square root of 2 times k, which is going to be 4.5 times 10 to the 3, times 1.602 times 10 to the minus 19 joules per EV, times a mass, oh man, the mass, what is it, 9.11 times 10 to the minus 31 kilograms? You'll have to check me on that. I didn't write that down. I solved this problem with AstroPi, so I didn't actually figure out what that was. The charge is 1.602 times 10 to the minus 19 coulombs times B of 0.325 Tesla. All this comes out to be 6.96 times 10 to the minus 4 meters, or that's 696 microns. So just tighter than a millimeter. What's that? All right, good. I was scraping the bottom of my mental barrel to get that one out. There's a movie that a lot of the movie takes place in the British Parliament. And one of my favorite things, because British people are notoriously polite, even when they're saying something very mean, or at least that's the stereotype. And in the movie, one of the parliamentary lords says, if my fellow lord continues to scrape the bottom of the barrel for reasons to continue this trade, I'm afraid he will be under risk of getting splinters under his fingernails. And I was like, that is awesome. Well done. That's not the charge. It's because the way we derive electron volts is the charge of the electron. The conversion of EV to joules is the same as the electron charge. So it's by the definition of how EV is defined. Find the frequency. Here, the frequency B, in part B, F is going to be equal to, I think I had this backwards actually on my solution. Let me pull up here, or maybe my slides were backwards. Oh man, I don't remember. I remember there was an issue, and I'm not convinced that I fixed it after class last semester. So let me pull this up really quickly. Just in case I have absolutely boogered this up in terms of our definitions here. 2 pi r over v. We said that frequency is kb over 2 pi m. Frequency is kb over 2 pi m. Mass times... No, I guess that's right. Frequency is going to be kb, or qb, over 2 pi times m, and that comes out to be 9.09 times 10 to the 9 hertz, or per second, or that's going to be 9.09 gigahertz. And T, which is equal to 1 over F, is going to be equal to 110 picoseconds. So faster than a computer can think. Most off-the-shelf computers keep time on the order of nanoseconds. So this is a fraction, 1/10 of a nanosecond. No. Yeah, and they keep better time than the CPU does. That's interesting. Time cards. I never need precise timing, but it might come up. T is how long does it take to complete one revolution? So T, for it to go from here all the way around to here, takes 1/10 of a nanosecond. And gigahertz, or hertz in general, is just how many times it does it every second. So it completes 9 billion, right? Wouldn't that, yeah, so it completes 9 billion orbits every second. Faster than a Beyblade, right? Beyblades are pretty wicked, but I don't know if they're that crazy. I make that reference because I found out last semester in my Phys 2 class, Beyblades came up. I was thinking, that was popular when I was like 4 years old. It's amazing to me that it's come back in popularity, and like there's a whole meta on best builds for Beyblades and all this other stuff if you're in competition. I'm like, I don't have enough time to worry about that, but that's really funny to me and great that people do care about that. Let's go back into to slides on new material, okay? Funny that y'all were asking me about coffee. Now it's my turn to ask you guys about coffee. Yeah. The X points away from you. If you're seeing a field of vectors, X is going into the board. Because you think of vectors as an arrow, and what you're seeing is the back of the fletching of the arrow. Yeah. And then if it's dots, it's coming out towards you. Do what? I mean, water is great. I guess that's like life fuel, right? But I've never heard anybody say like, I got a big study session ahead of me. I got to go down some water. The problem with water, in terms of it being great for your health, like drinking this is good for my health in terms of hydration and in terms of making me move, but it also makes you have to use the restroom, and that takes away from study time, and like it's always a catch-22 when I'm in research mode because I want to be moving from my desk as infrequently as possible, but that's apparently not healthy. I've never thought so hard I started sweating. And I have what I thought was that I thought so hard I got a headache. But what I found out is I was thinking so hard I was refusing to eat and drink, and that causes headaches. I asked a biologist, someone who's familiar with neurology and the brain and human biology, he's like, yeah, it's impossible to think yourself into a headache. It is possible to think so hard that you forget to do the things that are important to biological processes, that in turn will give you a headache. To think yourself into an ulcer? Yeah. I mean, with you cause so much stress that, yeah, absolutely. But a headache, apparently not. Yeah, got to keep up. Your brain is using a lot of your body's resources, right? So, got to fuel up. If you don't have a brain, then go see the wizard. The Wonderful Wizard of Oz. Follow the Yellow Brick Road. I'm not sure where that is on campus, but you know, it is out there somewhere, waiting to be engineered by all you wonderful engineering students. Something somewhere over the rainbow. I don't know. So many different analogies that you can make. But as far as what we need to be concerned about, magnetic torque. Magnetic torque is derived, you can see the book for this derivation, but it's very similar to the torque that we derived on electric dipoles in an electric field. So I left it out here, considering it's the more or less same derivation. But torque is equal to mu, the magnetic dipole moment, or the magnetic polar moment, crossed into the magnetic field B, where for a current, the magnetic moment is equal to big N, the number of turns in your current loop. So if you just take a wire and you continue to loop it over itself and over itself and over itself, you count the number of loops, then that would be N times I, the current, times A, the area that the loop makes, times N hat, which is the direction that is normal to the plane of the loop. So torque, at least the magnitude of the torque, is going to be NIAB times the sine of theta. Yes, because it's a cross product, right? It comes from the definition of cross product, which is proportional to the sine of the angle between the vectors. You will never change geometries and all of a sudden what you thought was y means sine, all of a sudden becomes cosine. No, it's not one of those cases. Or I should say correct, it's not one of those cases. I mean, maybe mathematicians will arbitrarily change the definition of sine and cosine on us, but I have a feeling, I'm not worried about that happening anytime soon. If you want a fun set of special functions to study, you should study the hyperbolic sines, cosines, and tangents. Those are fascinating. What? Yeah, they're based on exponentials, but so are sine and cosine, right? Yeah, sine and cosine are based off of exponentials raised to imaginary powers. And so hyperbolic cosine is e to the x plus e to the minus x over 2. Cosine is e to the ix plus e to the minus ix over 2. Yeah. Sines and cosines and tangents are just exponentials with complex arguments. Learn something new every day, and you came to physics class, and turns out it wasn't physics that you learned. This results in a potential energy that is minus mu dot B, or that's equal to minus mu B cosine theta. Mu is the previous slide, is that magnetic moment that you would call it. That's going to be NIA times the normal vector. Yeah, the last one was magnetic torque, magnetic potential energy. Well, n hat is tucked into this right here. It's tucked into mu, right? I mean, it's the only reason mu is a vector is because it's pointed in the direction that is perpendicular to the plane of the loop. The cosine part comes from the fact that it becomes minimum. The potential energy goes to a minimum when B and N are aligned to one another. A current carrying loop is placed in a uniform magnetic field. How does the magnetic torque on the loop behave? All right, so the correct answer is the torque seeks to align the plane of the loop to be perpendicular to the magnetic field. I'll give an explanation of that here in a second, but it's not the first answer. The torque is 0 if the magnetic field is parallel to the plane of the loop. If the loop looks like this and makes a plane and the magnetic field is parallel to that plane, the normal is pointed up this direction. That means the normal and the magnetic field that is going this way are then perpendicular, and we defined it in terms of this direction, not the plane of the loop here, but perpendicular to the plane of the loop. So it's not the first one. The second answer, the torque is maximum when the magnetic field is parallel to the loop's magnetic moment. No, if the magnetic moment and the magnetic field are parallel to one another, take the cross product and the torque is 0. So the torque is minimum when the magnetic field is parallel to the loop's magnetic moment. For the explanation on the correct answer, we recall that torque on a loop is mu cross B. Therefore, torque is 0 when mu is aligned to B and mu is perpendicular, let me go back here. Torque seeks to align the plane of the loop. So basically it's trying to get these two things to be lined up such that the force is 0. The force is always non-zero and will always force the magnetic moment towards being parallel to B if they are not already aligned. Yeah. So before, if the magnetic field was this direction, right, then what's trying to happen is it's trying to orient the loop such that it looks like this, right? But what actually happens if we started in the first answer, right? If this was my initial condition, what happens? Well, it's going to start bending over like this, but absent of an energy loss mechanism, it's actually going to flip all the way over because it's got kinetic energy as it passes through this point. And so it's going to flip over, but then the torque is still going to do this, and it's going to start oscillating back and forth like so. Now, if there's an energy loss mechanism, it's going to act exactly like a pendulum, right? Eventually, those oscillations are going to get less and less and less, and you're going to get it to settle down to this configuration right here. Yeah, it's the exact same as the electric torque on an electric dipole. Yes, exact same. Good. Okay, the last thing we need to talk about from this unit is the Hall effect. The Hall effect is created when you have a finite-sized conductor and you allow current to flow through that conductor in the presence of a magnetic field that is perpendicular to the current. Okay? So there is a voltage maintained across this rectangular conductor here, right? There is a voltage maintained across this conductor because there is an EMF present, which means that the current is going to flow from left to right across this conductor. But if you imagine, let's forget that it's, let's look at this side A here, right? Side A, if we look at the positive charge carriers, imagine that it's not electrons that carry the current, but it's a positive charge carrier with the convention of our current direction, then each of those positive charge carriers is going to have some velocity across the conductor. The drift speed that we talked about on Tuesday of last week, or Thursday of last week, right? That there is some sort of drift speed of the charge carriers across this conductor. But we discussed that if there is a magnetic field present, then I take V, which is to the right, cross it into the magnetic field that's going into the board, and those individual charge carriers are going to experience a force. And so what you get is that you're going to get an abundance of positive charge on the top side of this conductor and a lack of positive charge on the bottom side of this conductor. And so even though there is a maintained potential from the left side of the conductor to the right side of the conductor that's causing the current, you're going to get an additional potential across the top and bottom of this conductor. We would call this secondary potential across the conductor the Hall potential, and it is due to the Hall effect on the charge carriers in the conductor itself. So the potential across the conductor, yes, would be equal to or proportional to this EMF here, but you get a secondary potential going from top to bottom across this conductor due to where the charge gathers based on the separation of charges. Okay? Now the only problem is, let's see here. If we think about this in terms of here, you get Q going back this way with some drift speed. The force is down and it goes up. I feel like there was some issue with this. I know what the issue was that is not well explained in the text. Part A is what would happen if the charge carriers were positive, right? But reality is our charge carriers are negative electrons. And so what is shown in the top figure here, or in the left figure, is incorrect, meaning that you would expect the positive charge to gather on the top and the negative charge to gather on the bottom. In reality, what happens in this scenario is that the negative charge gathers on the top and the positive charge on the bottom. Because we don't have positive charge carriers, we have negative electron charge carriers. Yes? W is the width of the conductor as shown right here by the cursor. EH is going to be the electric field associated with the Hall effect. So you see that looking at B being reality here, right? And in balance of charge, electric fields begin on positive charges and terminate on negative charges. So yes, due to the external EMF, there is an electric field going from left to right in both figures, A and B. But looking at B being the reality, you would get an electric field from left to right and an additional electric field from bottom to top. So instead of the electric field being, in this case, just pointed to the right, the electric field, net electric field, is going to be up and to the right, where it's going to be ever so slightly pointed up due to the separation of charge here. That Hall electric field is going to be equal to, and you can see the derivation of that, is equal to VD, the drift velocity, times B. What? VD is the drift speed of the charge carriers. Basically, we're looking to balance that the magnetic force is pushing us up, but we have to balance that out at some point. Once this comes into equilibrium, it means that the force due to an electric field has to be equal and opposite to the force due to a magnetic field. And we get that EH is equal to velocity times magnetic field strength. Comes back to what I said of the velocity selector. Same kind of thing. You want the electric force to be equal to a magnetic force. And that happens when the electric field is equal to the velocity of the charged particle times the magnetic field strength. So this helped us verify, or let me ask this, and I've already said it several times, even just in explaining this slide, but what major discovery did the Hall effect lead us to? Yeah, the charge carriers are negative. If charge carriers were positive, you would expect this scenario right here, but what we measured was this scenario here, and you get that negative charges are the charge carriers. Good. Using the definition of current as it relates to drift speed, then we get all of this right here is just derivation for the Hall voltage, the Hall potential, if you will, is equal to the current times the number density of charge carriers times the thickness of, the time it takes to travel across your system times the charge carrier times B. So I is current, N is going to be, T is thickness, not time. Width and W and T are width and thickness. So I divided by number density, so number per meter, cubic meter, let's say, times the thickness of your material, times the charge of your carrier, times B. And this is measurable in the lab. We actually have one of the professors, physics professors right now, is trying to induce a Hall potential across a plate of gold in one of his experiments to get to measure a certain optic effect. So it's pretty cool. Dr. Davidson, if you're interested in this, Roderick Davidson. A is the cross-sectional area. So in this case, it's going to be W will be the cross-sectional area times the thickness, which is going to be in and out of the screen here. Yes. N is number density. So how many charge carriers fit per cubic meter, per cubic centimeters? Yeah, William. Yeah. In a sense, you can think of, now granted, as soon as you turn off the electric field or the current stops flowing, then this Hall effect goes away, right? If the magnetic field or the current go away, then the Hall effect goes away. But right now you do have two sides with unequal charge distribution, which is similar to a capacitor, yes. Now, there is not an air gap or a vacuum gap between these or a dielectric gap, but there is non-uniformity of charge, yes. E is the elementary charge. So the charge of proton and electron. 1.602 times 10 to the minus 19 coulombs. In the Hall effect, what is the primary reason a Hall potential difference is developed across the conductor? Yes, it is that the charge carriers experience a force perpendicular to both magnetic field and current. Number one, we're going to talk about magnetic induction. Magnetic induction is a little bit different here. It comes from the interrelationship between magnetic and electric fields. But that is not what's going on here. It's physically how the charge carriers are affected as they move through a conductor. And it comes from the Lorentz force, F is equal to QV cross B. And this is going to cause the charge carriers to deflect to one side, leading to an excess on one side and missing charge carriers on the other side. Any questions either out loud or on your devices? I know we've already done this once today, but might be new questions based on what we've covered so far. Yeah. Yeah, if you ever see something that is typically defined or has been defined as a vector, but you see it without the vector hat over it, we're just talking about the scalar magnitude at that point. Good question. If you ever see something that is defined as a vector without the vector dagger over it, then that means that we're just talking about the magnitude. What am I having for lunch today? I don't know. Do y'all have any recommendations? I was thinking Chick-fil-A. I left my lunch at home, as is the custom for me. Absent-minded professor, the last thing that I'm thinking about when I'm saying goodbye to my wife and children, I leave my lunch at home almost every day of the week. So, Kava? Never had Kava before. I've been there actually. I bought a gift card for one of our kids' preschool teachers. It looked really good, but I just ran in and out. Kava sounds good. But you've got Kava, which is healthy and good options, or you've got fried chicken and fries. It's hard to compete with. If what? Beast mode. Really? Where do they usually park? Mondays and Wednesdays. Okay. Well, somebody message me the next time they're on campus, and I'll go check it out sometime, okay? Any video recommendations for the Hall effect? No, I'm not aware of any. I would just look on YouTube. What is W? It's the, 23rd letter of the alphabet? 22nd? No, just kidding. It's in the equations, it's width. So the actual width of the conductor. Let's see. If you had to make a physics-themed band name, what would it be? I don't know. I'd have to think about it. I'll tell you next time. I think that's everything. Best magnetism pickup line. What's up? Y'all have a great day. See y'all later. Y'all have a great day. What's up, Dave?
I got a question. So